So we're ready to start. Using VPP and SR-IOV containers and over and array for it's going to have a baby. Okay, sure. So Manohar is a principal engineer for Intel's Open Source Technology Center. We have been working on networking, network management, network processes, and virtualization for over 15 years. He is currently an architect and developer with the CIO, Clear Dynamics CIO, and the Clear Containers project focused on networking. He has spoken at many container meetups and internal conferences. So I give it to Manohar.
Yeah, hi. So as part of this talk, I'll be giving you an overview of layer containers, what layer containers are and how, and we'll also show you a couple of examples where layer containers can be used in the context of network function virtualization. In this track, today there have been a few sessions on VPP, microservices-based DNS, things like that. So this should hopefully be a good follow-on to people who have been on this track. So at the very end, maybe 15 minutes or so, we're doing a hands-on sessions where you can actually try a lot of the things that I'm going to talk about. So first things first, right? So what I'm going to talk about is a very brief look at DPDK, VPP, SR-IOV, and a brief introduction to layer containers. I know that some of you must have sat through the DPDK session, VPP session. So I'll just quickly go through it. I won't spend too much time. Then we'll show you how you can create a DNS chain using layer containers by using a combination of VPP and SR-IOV. And there's a hands-on lab at the very end where you'll get access to servers of your own, I mean, a virtual machine of your own, where you can try layer containers with VPP that you just heard a few minutes ago. So, this overview of layer containers. So, before I go into layer containers, how many people here have used containers? I mean, Docker containers. Okay. Almost half. That's okay. So, first things first, right? Containers are very popular right now. The whole reason they're very popular right now is using containers gives you a very nice way of packaging of your application and your application dependency and being able to deploy them very easily on any given machine. So you can deploy your applications with very little difficulty on any OS. You can run the same application bundled in a container on Ubuntu, Fedora, CentOS, or any distribution of your choice. So you can go from pulling an image off of a container repository like Docker Hub to have it running in less than 1 second, leave out the time it takes to actually pull the image. When you compare that to virtual machines are normally packaged using virtual disks, which are mostly around 1 gig or half a gig. They take time to get deployed, they take time to bootstrap and run. With containers, you can get an application packaged in a container up and running in around 1 second. So that's the reason why people love containers, the packaging and deployment aspects. The key thing is when you look at how containers work, the way they work is all containers running on any given machine share the same Linux kernel, and they are separated from one another using two Linux kernel capabilities. One is called namespaces for doing isolation between containers, and C groups to actually isolate the resources between containers. That each container gets its allocated on CPU time, memory, and things like that. So the key thing is now there are multiple containers running on the same host, sharing the same Linux kernel. one thing that you have to keep in mind is, if the kernel that is running gets compromised by the application running in the container, it brings down the whole machine and potentially compromises the other container running on the same host. So when you go from virtual machines to containers, you're going from security that's built into hardware, which is normally Intel VPP, to security that is implemented using software, which is just the Linux kernel. So you've got the entirety of the Linux kernel which you can try to complete. So what clear containers tries to do here, on the far end you've got virtual machines which are perceived to be slow, pretty large, slow to boot up, hard to deploy, and at the far end you've got containers which are very simple to deploy, but they do not offer the same degree of security and isolation as containers. So the containers tries to fill that gap. So now you can deploy containers with all the container tooling, deploy package and run containers with all the container tooling, but the actual isolation between containers, in the case of clear containers, is using the same technology which is used to build out virtual machines. So here is an example of how containers look again with regular namespace-based separation. So what clear containers does is, when you actually launch a container using a clear container, each container is launched in a very thin, lightweight virtual machine. And inside of the virtual machine, each can get its own copy of the Linux kernel. And on top of that, you run the exact same container workload that you would have run using Docker run, for example. You can take any container image that you can find on Docker Hub or the Google container repository or Amazon container repository and run it. But at the time the container is launched, it is run inside of a very lightweight, very thin virtual machine. And one more thing is, now you are fully isolated, and every container comes with its own kernel. So if there is a kernel vulnerability, the exploit is limited to that small virtual machine. It cannot compromise the host, or it cannot affect any other container that is running on the same host. So there is one more property. Now the kernel that you are running in the container is different from the kernel running in the host. So for example, you can run the greatest kernel for the container, whereas the host system can continue to run your qualified kernel for your given kernel. So this lets you run either a custom kernel or the latest kernel, or for that matter any kernel, on any machine without provisioning your bare metal orders. You can continue to run your qualified kernel on your machine. The second thing is, to be able for us to have this very thin-weight, lightweight VM, we have created a very minimal machine type called PC-like. This is just enough virtual machine to run container workloads. It's all .io if people are familiar with it. So it doesn't have any legacy devices modeled on it. And also the Linux kernel that we run inside of the container is a very minimal kernel. It's a very small kernel. So the trusted computing base of that kernel is also very small. We're not having a kernel with all the legacy devices, hardware devices and things like that a normal kernel carries. What ends up happening is, we can now run containers with as VMs with almost no difference. So, for example, a regular container boots up 600 milliseconds. A clear container roughly boots up around 800 milliseconds, and I will show that to you. So, there's only a 200 millisecond delta between a regular container coming up and running versus a clear container. In terms of memory footprint, we are around, for every clear container, we need 30 MB of extra memory for the clear container, to run the virtual machine, to run F1 copy of the sun, and things like that. But if you run an application that consumes a few hundred MB, the 30 MB differential between running a container as a bare metal container as versus running in a clear container is marginal. In terms of storage overhead, we use the same graph drivers and overlay file systems that are used by containers. So there is no extra storage overhead by running containers. You can use, on a given machine, we can run containers as well as clear containers using the same storage framework that is built into containers, which by the way is very efficient. So a container image consumes maybe 40 to 50 MB, and if you got 100 containers running that are based on the same image, they typically do not consume any extra storage, unlike VM. And we keep all the properties of containers. So the thing with clear containers is you have all the benefits of VM and all the benefits of containers. So you don't sacrifice either the container goodness or the virtual machine goodness. So, okay, so that was a brief overview of clear containers. And okay, so now let's go on to what we wanted to cover here, right? All that is involved. I got this fast, secure container. So why does it matter? So traditionally, I mean, virtual network functions have been implemented in VM, right? In case of telco use cases, you want high reliability, you want you normally run a customized kernel, you have optimization, you tweak the kernel parameters to have very low latency, and there are use cases where your virtual network function just isn't throwaway. It's not like a regular function. It doesn't come and get destroyed, and it doesn't run for a few seconds and go away. You're running it for a sustained period of time. And most people run your virtual network functions in VMs today, right? So what clear containers lets you do in this particular use case is you can now leverage all the efforts you're putting to VM technology, things like VPOS, SR-IOV, DPDK, VPP, which have quite a bit of support for VM, and you can leverage them using containers, using clear containers. So this is just a very simplified example for what could be a virtual network function chain, right? You've got packets coming in, they're getting processed through a series of virtual network functions, and they're getting sent out. This is a simplified example of a virtual network function chain. So if you want to realize that, so we just give them all names. Today you can construct this pipeline if you wanted to using regular Linux containers, if you wanted to. Why wouldn't you do that? So why not just use the standard Linux networking that comes with containers? So if you, I think in the previous presentation we talked about the requirements for packet processing for virtual network functions, right? So on to process one packet on a 10 gigabit link, you want to sustain a 10 Gbps throughput, you get roughly 67 nanoseconds to process it, which leads to around 201 cycles if you're running it on a 3 gigahertz CPU. And if you take a look at time accounting, the time it takes for you to access data off the I2I3 caches, and how long it takes for you to access memory, bulk of your time is consumed just in getting the packet in and out. That's where using something like VPP is very useful, because it kind of amortizes this cost across multiple package, right? So for this we have got DPDK. I'm not going to talk about DPDK. We already had a good overview of VPP, which does this very efficiently. So anyway, I won't talk about it. We just had a question. So there's one thing that I don't know if it got covered earlier in the lecture today, which is SR-IOV. When virtual machines became popular, most networking vendors and in the PCI aspect, there was a new concept which is single root virtualization, where you can now take a single physical network interface, create multiple virtual network interfaces, and then assign them directly into virtual machines. That gives you a way to get packets into a virtual machine as fast as possible. At the same rate as how fast the packet would have been injected if the networking stack is running on bare metal. So with SR-IOV, you use lots of high-end network card support. If you can partition a physical network card into multiple virtual network interfaces, and you can assign those virtual network interfaces into virtual machines. So what this really means is you get a very low latency path and high bandwidth path for packets to get into a virtual machine and out. And because clear containers is actually implemented in the virtual machine, we can leverage things like SR-IOV even with clear containers, even though they are uncontained. It's a bus device function, PCI video. Okay, so now I just very quick fast hit on containers, clear containers, some of the basic packet acceleration technology, right? So now I just want to bring it all together and show it to you working next, right? So let's just say you wanted to achieve this virtual network function chain using containers. So what would it look like, right? So if you were to do this with traditional VMs, one way to do it is one of the fastest ways to get packets from the host into a VM, short of doing SR-IOV, is something called vhost user. Vhost user is something that is supported by VPP as a means of injecting packets into a virtual machine at the fastest rate possible. You can there are implementations for both L3 switches and L3 routers or L2 switches built using VPP. That can serve as a means of getting packets into the virtual machine as quickly as possible. And also, it can be used to actually connect a series of virtual machines together. So you can create a virtual network function pipelines that look something like this. So you've got vhost user getting packets from the network card, pushing it on, and then you use vhost user to send packets between virtual machines. So this lets you process parts of the pipeline in each VM and then send it over to the next virtual machine to do the next set of process. For example, in one place you can do encode followed by encrypt. Then maybe if you're doing some kind of media pipeline, you can do your multiplexing and then sending the packet stream on. So this is how people normally construct these virtual network function pipelines. So a slightly even faster way to do the same processing is you can get packets into the first VM using SR-IOV. So you get packets directly from hardware. They can go into the virtual machine. You get processed in the virtual machine using the regular networking stack. So inside of the virtual machine, you see two network interfaces. Regular, they get IP addresses. Then you run some kind of application, a firewall application, or maybe IP table do something like that to process the packet. This is one possible way you can construct the pipeline. And here I'm showing packets coming in over SR-IOV, getting processed using the standard kernel space network stack, then getting transferred across virtual machines using the VPP cross connect switch, and then going out again over SR-IOV. This is one. So, and if you want to do things even faster, what you can do is you can get packets in over SR-IOV. You can choose, now you are completely bypass the kernel stack on the host. The packets are being injected straight into the guest virtual machine. Inside of the virtual machine, you might decide that the kernel stack that's running in the virtual machine isn't fast enough. In which case, we can actually run a full mode driver and the DPDK full mode driver. On top of that, you can use VPP to do packet flow. So now all you are using your virtual machines are for packaging your application. So now you can get your packets in through SR-IOV, process them purely in application space inside of the virtual machine, send them out directly from user space onto the host. On the host side, again, it's being processed completely in user space and then sent. This is potentially the most efficient way, at least most latency efficient way in which you can chain a set of network functions to do packet processing. So what I'm going to show you over the next few minutes is, because Slave containers now are also VM, I'll show you a way to construct these sort of pipelines using a combination of Slave containers, SR-IOV, and VPP. So what we have done is, just to show that how you can do this, we have created a set of plugins. We have created a plugin for OVS DPDK, which is one way to do packet processing. And this plugin lets you replace the default Linux bridge that comes with Docker with a bridge that is based on OVS DPDK. But I'm not going to do a hands-on of that. The actual hands-on we're going to do is, we also created a plugin for Docker that uses VPP as a replacement for the Linux bridge. So this lets you do much faster packet processing when transferring packets across containers running on a given patch. So this is much faster than the Linux bridge, and more importantly, I've got much better latency than the Linux bridge when you do packet processing, linking a set of containers together. Very similarly, we have one more plugin for SR-IOV, which lets you do direct connection of an SR-IOV interface into containers. Now, all the code for that is fully open source, and you can get it from GitHub. By the way, Slave containers is also completely open source, so you can get Slave containers as well as these plugins and play with them offline. And also the demos that I'm going to show are also open source, and the source code for all the demos that I'm going to show you is there on GitHub. So before I go into the demos, do you have any questions either on Slave containers or generally using DNS for build containers? CRM is Docker has got a specification of how do you create software-defined networking for containers. So that's called container network, forget model. That's the way you kind of abstract a software-defined networking. If you go with Kubernetes, there was something called CNI, Container Network Interface. So these are abstractions on how you implement software-defined networking for containers. That's the guy. I get that question a lot. Their containers isn't really a replacement for Unicron, because in case of Unicron, typically you run a custom application that runs directly on virtual hardware. With their containers, if you look at the model that I spoke to before, where you have a full mode driver, right? So Linux kernel itself is providing very little functionality. In the sense that it is just giving you the capability to talk to a device. It is really not in the way of packet code. So in this case, when you offload most of the functionality into the user space in their container, it almost starts looking like a unique kernel. But we still believe that having a full-fledged kernel running inside of the Play container environment is better for most people, because you get the standard Linux kernel ABI. You can take any container that's on the web or run it in a Play container. Whereas you went for a unique kernel, we will only be able to support custom-built applications for that stuff. Right? So can you do unique kernels using the Play container framework? Yes, because in case of Play containers, you can replace the kernel that you provide with a unique kernel. But then, how the land applications, I wouldn't know. I know that Docker is working on their own unique kernel, and we haven't looked at what will it take for us to run that unique kernel in their container, and whatever applications that get bundled with that unique kernel in this environment. So this isn't a unique kernel. This is an extremely lightweight virtual machine. So the first thing that I'm going to show you is just running Play containers on a given machine. So, let me reconnect. Looks like my machine went down. Okay, so the first things first, right? This is a regular Fedora machine running Docker. On this machine, what we have done is, Docker comes with something called the default OCI runtime. What we have done on this machine is we have set the default runtime for Docker. What runtime means here is the thing that achieves the software isolation between containers. It is responsible for providing isolation between containers. So on this particular machine, I've said that by default use the clear container runtime, which is QR, as the default isolation mechanism to separate out containers. So let me first run regular containers. So you guys can see this. Because the default runtime has been configured to be clear containers, I'm saying explicitly, please run this null-file container using the standard Linux namespace container. So let's just run this. And it takes around 600 milliseconds to launch a regular container on this machine. So next what I'm going to do is, let me run clear container. Because the default runtime on this machine is set to clear container, and by not providing any explicit runtime, the container is launched as a clear container. So, okay, so around within 200 millisecond differential, you are able to launch a clear container. But keep in mind, in this 797 milliseconds, we have launched the VM, we have launched the application that constitutes the container inside of that VM. So if you quickly look at this, we have actually, this is a bit intense, but we have launched a VM, and inside of the VM, we have launched a container. So just to show what it looks like, right? So on this machine, now I've got two containers running, one regular container and one clay container. Let us run one more regular container, and this time I won't run the container in the background. And this is a regular container, and if you notice, it shares the same kernel as the host. Let me go out from that, and let me now run clay container. If you look at this, it is running it doesn't share a container with the host. It is running its own kernel, but it has all the properties that have been set up for the container. It's an Alpine container with full networking, full storage, all of that. So now I just showed you running. Okay, I ran an Alpine, right? I'll just show you how simple it is. I'll run them in the background again to run pretty much any container that you want, right? I ran Alpine. Now let me run Ubuntu. So you have a so it is running Ubuntu. I ran that interactive, but I'm just showing you, let's run it non-interactive, right? So run Ubuntu. Okay, in around 780 milliseconds, you had a Ubuntu clay container up and running. Let's try Fedora. Same time, around, so basically you can get a VM running a container with the same, roughly the same footprint as a regular container using clay container. And just keep doing this, right? This is my just workstation. I'm just showing you how many containers I can run. Remember, each one is running a VM. At some point, it will run out of memory, but so how many do I have? I don't know. I've got, this is a regular workstation that I'm running on. And in terms of density, let's say on a high-end server, you're able to run, I don't know, 200 containers, real workload doing the real work. In case of clay containers, based on the workload, you might be able to run 200, maybe 180. But it isn't like you can run 200 containers and you can run only 50 clay containers. Maybe 20% less clay containers, primarily because you need around 30 MB more of memory per container. But that's about the only density in the console, right? So I just wanted to show you what clay containers looks like. And just to kind of follow, we have clay container packages for Fedora, Ubuntu, CentOS, Linux is their own distribution. So all it takes for you to provision clay containers on any system that on which you're already running Docker or on Kubernetes to install a package. As simple as DNS install, apt-get install. And then on, if you specify our runtime as the default, everything is transparent. Your developer workflow is transparent, your provisioning is transparent, you can use Kubernetes, you can use Docker Swarm, you can use Rocket, any any of those popular container runtime. So nothing changes for it. So anyway, that was a quick demonstration of how clear containers looks and feels like. Right? So next, let's go into showing clear containers working with SR-IOV and with VPP. So the first thing is let me show you SR-IOV. So, by the way, this demo is on GitHub. I'll send you pointers if you want to replicate this demo offline. So, the first thing that I'm going to show you is something like this. I've got two machines with each one having one NIC that is capable of supporting SR-IOV. They're directly connected to one another. What I'm going to do is I'm going to launch one clear container on one machine, second clear container on second machine, and push packets from one clear container to second clear container over SR-IOV. So on the first machine, let me first what I'm going to do is I'm going to set up a Docker network that supports SR-IOV. You can ignore the rest of it, but the key thing what I'm doing in this demo is I'm creating a Docker virtual network, and I'm creating a VLAN-based network with a VLAN tag of 100, okay, and I'm giving it a subnet of 192.168.0. So each time you launch a container that's part of this SR-IOV network, it will get an IP address from this range. So now I'm going to launch one container on one host and a second on another, and I'm going to connect them using SR-IOV. Take just a minute. Okay. So first thing is on this machine, I've got a dual ported Intel NIC. Each port supports 10 gig, and both these ports support SR-IOV. If you take a look at the maximum virtual interfaces that each port supports, they support a total of 63 interfaces. So in theory, you can create 126 containers that can use SR-IOV on these two ports. But all I'm going to do first is I'm just going to provision one virtual function on each NIC. So now if you take a look, you'll see that I've created two virtual network interfaces on this machine. Or if you want, I could have created 63, but just to keep this demo simple, I've got two virtual network interfaces created on top of the two ports that are already present on the system. Okay, so now I created a Docker network, or Docker network, as I mentioned, with a VLAN ID of 100. Now let me go to the second machine and do the same. Here I'm not going to print any debug messages. Yes, so the plugin we have written works with regular containers and with it's transparent. If you use regular containers, what happens is the network interface gets created on the host, gets fully programmed on the host side. In case of clear containers, we use VFIO. Using VFIO, we do PCI direct device batch assignment of the SR-IOV device directly to the play container. So what that means is, now that the PCI device is assigned into the play container, you've got two choices. You can run a regular networking stack. You can run the standard Intel NIC driver, and you don't see any difference. But let's say you want to use VPP, then you wouldn't run the standard Intel NIC driver. You would run the UIO driver and just run VPP on top. So now you can take packets directly from hardware and consume them in VPP running inside data. So basically there's a zero overhead packet transfer from hardware into the application space of play container. So now I've gotten the same thing set up on this end. So let me run a type of server on the first container. Going back to the previous one. So now I'm actually running traffic. So now I'm getting traffic getting transferred across the 10 gig net across two play containers, getting close to line rate. On a lab network, so some other traffic going through it. But you can get the same latency as you would get from raw hardware. But keep in mind, in this case, we are using the regular Linux kernel stack. If you wanted to beyond 10 gig, you definitely need to look at something else like running VPP in the play container itself. So this is the first thing. I just want to show you how play container leverages VPP. The next thing that I wanted to show was virtual network function chain that uses VPP. So what I'm going to show you next is a set of 3 clear containers which chain together using VPP on the host to get packet acceleration going from container A to container C. So if you look at this logically, you can run some kind of networking logic in each container, fully independent of any other container. And in this case, I'm showing VPP handling the packet processing on the host side. In theory, you can even run VPP inside of the play container. I don't have that. I'm not going to show that here, but that's the thing that you're going to show next. So let's see. So in this case, what I've done here is I've created a virtual network function chain that consists of 3 containers. Yeah, the container A, B, and C, which are linked in the manner shown above with VPP. And let's go into one of the containers, container A. And from here, what we can do is we can reach across this virtual network function chain and send traffic from container A to container C when all the packet is getting, all the traffic is getting accelerated using VPP on the host. So this is container A. Before doing that, I just want to know what the IP address is of container C. Container C is 2.10. Okay, so now we have packets flowing through this virtual network function chain, and just a minute. Let's take a look at how VPP has been configured on this setup, right? So you have, as I mentioned before, you got 4 VPP network interfaces configured here, and they are actually spread across it's show bridge, right? I forgot the command. It's got 2 switches in the same machine. I want to show the 2 switches. Oh. Yes, this is it's got a mean. So the traffic is flowing. I mean, I would like to show that it's all going through your.
So where the VPP state? Are these staying in a container?
So in this case, they're showing VPP is going. Here we are using packet acceleration to get packets in and out of the container. So we are only getting one part of the stack actually. So if you want the most efficient way to get packets through the chain, you would actually do VPP on the outside as well as VPP on the inside. So you can get packets in and out and processed using the most efficient manual process.
Outside,
on the host. Yeah, right now we're using VPP on the host.
Why not you just
on the host?
Not using
running an old version, right?
Running old host.
You're running 1701.
Okay.
Yeah, that's all right. Oh, yeah, so you can see shirt running.
So the guy who was supposed to do the demo is on the baby.
Yeah, oh, yeah. Do you know what bridge domain it is?
1 and 2. Yeah. So if you notice, we got. But yeah, thank you so much.
Oh, we'll get anyway.
Okay, so we have actually created 2 virtual VPP switches, as I mentioned, and they used to create a virtual function chain that links all the containers together. So we have only gotten the part of the data plane ready, but the beauty of the approach is the container workload themselves are regular container workload. People got no idea that they're getting packets at a higher rate. But if you are writing a NF function, right, you would then create a custom Docker image with VPP built into it, take over the net, which take over the virtual net, and then do the packet processing in the container. So with this, we can seamlessly deploy some kind of VNF in clear containers.
VPP in the host, if we are doing SR-IOV and VPP.
No, we don't. Yeah, if you do SR-IOV on the host, and
I can directly do VPP.
you can do VPP. Okay, the question was if you're using SR-IOV, do you need VPP on the host? No, but then how will you get packets across a chain of VNF? If you've got a single VNF that is accepting and sending packets out to hardware, yes. But if you have a chain of VNFs set up on the same machine, in theory, you can actually send it out to SR-IOV, use the hardware switch built in hardware and push it out. But what we have found is it's faster and better and more scalable if you use the VPP switch in software rather than sending the traffic down to hardware and send it back up to a VM. Yeah, you're eating PCI bandwidth in that case. So if you want to chain network functions, at least the most efficient way we have found it is to use VPP. Because if you send it out, send it in, each hop of your chain is going to consume PCI bandwidth and you don't need it. Yes, this is using, actually that's a good question, right? So let me come out of this. So if you take a look at how the network interface is passed into the container, right? So this actually uses DPDK. So this is VPP with DPDK used to actually send in packets into the container. Actually, yeah. You guys are supposed to have a hands-on demo. I lost control of time, but there are VMs set up. I don't know how long they'll be on, but where you can try this exact same thing on your own. Yeah. So I'll be I'll do one thing. I'll send them all mailed out. Plus, on the meetup link, right? I'll post all the URLs. So all the demos that I've done, as well as the hands-on, can be replicated on your own. And the source code as well as the demo source code is on GitHub. Anyway, but this same demo can be reproduced on any of your machines. So we decided to make the demo as non-SR-IOV so that we can try VPP clear containers on any machine or a VM. So,
The demo VM will not be accessible outside.
Sorry.
Yeah, but if they want to pay later and do this,
Yes.
that's
Anyway, so I've got a couple more minutes of questions. So. No. So the question was when you use VPP with Kubernetes, right? So when you use clear containers with Kubernetes, the way it's set up is a pod is a VM. So multiple containers in a pod run in the same clear container VM. So now to interconnect pods and connect pods to the network, there are a couple of ways to do it, right? One, the simplest way that we think we should support is just simple all L3 pods, which is the default in something like Calico, where there is no matting going on, except for traffic that is going out to the general network, right? So there we are hoping that VPP someday will support Calico and we can just use it on the network. So all layer 3. We don't believe that doing matting is the best idea in this.
Turn it around a little bit. It's more about Calico supporting VPP because the data plane doesn't really understand the orchestration layer. And with that, we would love to see.
So just to highlight, that K containers works with any kind of network plugin, but in the case of this special network acceleration, that is not fully stream yet. So we are trying to work with the Kubernetes community to add in notion of packet acceleration